Okay, so in the beginning I'll edit the video to start. Alright. Let's start with the slide. Okay, so good morning everyone. So this is MKEL1283 Hardware Software Co-Design. The first module, the introduction module. So first we go over the course overview, what the course is about, and also the arrangement of the course, percentage of your grades and so on. Okay, and then we'll just take you to the introduction to SOC, FPGA-based SOC, approaches, and also the code design. Okay, so what the course is about? Basically, we have 3 meetings, right? 3 weekends. So the first meeting for this week, this first weekend meeting will cover the system level basics and test bench design. So mainly on verification. Okay, verification using system Verilog and also C program. Okay, kalau I think you have taken RTL before, it should be okay. And then maybe if you have not done C, or probably you have done C in other courses, right? So we'll be looking at for the first meeting, we're mainly looking at system Verilog and C++. Okay. Second meeting, which will be I think around May, right? Early May. So second meeting, we'll look at the optimization methods using system Verilog RTL to improve performance power areas, right? And then the final meeting, the third meeting I think around June. Okay, the final meeting around June, we'll cover the high-level synthesis methodology for FPGA. Okay. So I see Izzat in the front. I think you have taken my undergraduate course, right? So those graduates from UTM have taken my DSP architecture. We'll cover number 3 last time. Remember HLS? Ingat? You masih remember? Right? So, who has graduated from UTM? Ashraf, right? UTM. UTM, you taken my course as well, right? DSP architecture last time. Kita tak boleh? Who has graduated from UTM? Lain tak? Tak ada. 2 je. Okay, so I'm from UTM. Which part of the specialization is KEL? For telecommunication, I think you didn't take my. So normally in the ESD, if you have the ESD, electronic system design or computer engineering, normally you will take ESD architecture where we look at the high-level synthesis methodology. Okay, so this is the third part. But I would say the more challenging or the high value is more on the first and second part. So postgraduate we cover the first and second part there on the verification methodology and also the optimization methods. Okay, the third part here is mainly using the tools. Right, so we cover in the undergraduate, and I believe that most of the universities I think they don't cover HLS methodology. Okay, ataupun ada anything from other uni have covered HLS. HLS is converting from C to Verilog. Okay, you write the program in C, and then you generate your system Verilog code. Okay, instead of you writing the RTL manually. Alright, so basically the software hardware code design, we have the software part in C, C++, we write description in C, and also the hardware side, we look at the system Verilog, the SP. Okay, one thing I added here is the students are also expected to describe and explain concepts related to software hardware code design. So there will be a test or exam question related to the concept, what is SOC, FPGA, ASIC implementation, different software hardware implementation, and all these concepts. Okay, so we'll be using the design tools from Xilinx, the AMD Xilinx tools called Vivado and nowadays I think they call Vitis, Vitis HLS. So previously it was Vivado. I think since last 1 or 2 years they changed the name to Vitis. And then if I'm mistaken, by 2024 they have a new update. Okay, they have a new update on the tools. They integrate several tools together inside the Vitis. And the tutorial that I have is actually from 2023. I don't have time really to make a new tutorial for 2024. Need to uninstall and reinstall. But anyway, 2023, the tutorial that I give you later, we can do the tutorial. It's a 2023 Vitis. Okay, it's more or less the same. I think just just a tool integration in 2024. But these are the tools that we are going to use. Okay. So I don't know if you still have Vivado. Those have taken my class I think how many years ago? 2, 3 years ago, right? So that I installed. You still have the tool, is that? Or don't have anymore? Okay, so it is quite big. I think at least 40 or 50 gigabyte you have to allocate in your laptop. Okay, 40 to 50 gigabyte should be sufficient to install the things. Okay, so this is what we cover. So the hours there is tentative. Okay, I'm not going to follow exactly the hours, but basically we should cover total 42 hours for 3 credits. Okay, total 42 hours. And we have 6 days of meeting. So theoretically plus minus 7 hours per day, right? 9 to 5, today and tomorrow, and then for 6 days. Okay. Well, of course, we'll see how it goes. Okay, we'll see how it goes. But basically, we're going to cover for the blue part here for the first part, the first week. The green is the second meeting, and the red is for the third meeting. All right. So you can see there, for this week, we're going to cover more on the fundamentals of system Verilog. So I believe all of you have taken the Verilog RTL, right? Advanced Digital Verilog. So we see what is the difference, what are the features in system Verilog, how is it different than the normal Verilog. Okay, we didn't cover in undergraduate last time. So system Verilog we cover in the postgraduate. And then we look into more detail on verification method. Okay, the test bench. So this afternoon, so this morning, maybe the first one there, to our concept there, and maybe if you have time, a little bit on the system Verilog. If not, this afternoon we'll cover system Verilog. Okay, and then tomorrow morning we'll cover the test bench, and then tomorrow afternoon we'll do the DIC. Okay, all we'll see, if you guys are quick doing the exercise and so on. Okay, we can probably finish early, or we'll see how it goes with that. But the plan is tomorrow morning test bench, and then afternoon the DPIC. Okay, and then the next meeting, okay, we cover the optimization flow. Okay, optimizing the system RTL for area, latency, and also looking at the pipelining methods. And then the last meeting is on the high-level synthesis. Okay, so this high-level synthesis should be quite straightforward actually. Should be quite straightforward. Just using the tools, we write our system in C, and then we generate the RTL from our C description. Okay, so total 40 hours. Okay, as for the assessments, for this semester, we'll have 2 tests. Okay, test 1 and test 2. Test 1 10%, test 2 10%. The test 1 will be in the second meeting, and normally I do it in the morning of Saturday. Okay, normally morning Saturday, maybe around 9:15, something like this. Okay, and test 2 will be in the third meeting, also in the morning and third meeting. Okay. The flow of the class for the next meeting we'll discuss later. Okay, but we'll have the test 1, test 2, test 1 second meeting, test 2 third meeting. Alright, and then the projects, the group project. Okay, I already set up the group for the class. Later we'll see the e-learning side. We'll have 3 group projects, each one 10%. Okay. And normally for postgraduate class, I don't do a peer review. Alright, only for undergraduate, there are some issues with discussion with the group members. So normally we don't have the peer review unless there's an issue later on. But I never had issue. Alright, we will be postgraduate. You guys are more mature, right? So it should be no issue. So 10% for project 1. So project 1 I will give you this week. You review right before the second meeting. Okay, and then project 2 will be given during the second meeting. Will be due third meeting, right before the third meeting, and then you have a project 3 will be due around a few weeks after the third meeting. Okay, and then we have the final exam, 50%. Okay, a face-to-face final exam here in Penang. Okay, as usual. Okay, our main resource will be the lecture slides that I gave you. I posted it on e-learning already, and also the book that you have purchased, right? You have bought the books. Okay, so if you have your past semester, like if you use the previous book, is also okay. Also okay, there's just a slight difference. Okay, something to note, the test 1 and test 2 will be open book. Okay, test 1 plus test 2, normally I make it open book. But the final exam is closed book. Okay, so final exam 50%, because final exam we are not allowed to make open book. But the test is okay. Test, I think we can make open book. Right, we'll discuss more about that one later, what we'll cover in test 1 and test 2. Yeah, but basically test 1 will cover the first meeting. Okay, Saturday, today, that's test 1. And then test 2 will cover whatever in the second meeting. Right? Okay, so you can call me Dr. Hadi, officially, Dr. Hadi, and I'm at the MKEL1283. My phone number, my contact information is there. I also have a website about myself, what I do, basically my research side and my teaching side. And then we have the e-learning side. Okay. So for e-learning, I have posted several materials on e-learning. Okay, we have the course information here. I posted everything under general. Okay, I posted everything under general. Course information, and then these are the 4 topics that we'll go through. So we did today 1 and 2, and then tomorrow we'll cover 3 and 4. Okay. So assignment is also ready. All right. The assignment will discuss more tomorrow. What you need to do for your assignment 1. And then I also have the assignment group information. Okay, let's have a quick look at the group information. So I already put your name here. Okay, randomly. Okay, so I randomly put you into groups. Okay, so group 1, group 2, group 3, and then group 4. So group 4, we have 4 members in group 4 because we have part number. We have 13. We have 13 of you. So the last group, 4 members. Okay. So any issues with the group? You'll be okay? Okay. If you have issues, so postgraduate normally no issue. So I think you guys should be able to work together. No issues, right? Okay, but if you have issues, you just can let me know. All right. So this is regarding the information, and then this is the last semester test, not this semester one, not your test. Okay. So now your test will be different, but basically the same flow of concept. All right. Later, we will have a look into more detail on this one. I also posted the solution here. Okay. Just as a reference for you to prepare for your test later. All right. And then I also have the Vivado tutorials, and this one we need to do later on. Okay. So for the tutorial, the first one is how to download and install Vivado, right? In my case, so this one is just a PDF document on how to install rooms. And then number 2 here, so this is the first one you need to look or read through. And then number 2 is the basic tutorial on system Verilog. Okay, with Vivado. So basically a system Verilog design. The source code is all here. Okay, I think it's a simple header design. And then we have a test bench there. Just a flow of how to design and verify your system Verilog using Vivado. So this is number 2. Number 3 is the CRTL core simulation. This is the DPIC. Okay, so this one also you need to do for this meeting. Number 1, 2, and 3. Okay, so 1, 2, and 3 for this meeting. Next meeting in May will be number 4. This is optimization tutorial. Okay, how to optimize your system Verilog RTL using Vivado to analyze for power, performance, and area. Okay, so this is the video tutorial number 4. It's for the next one. You don't have to do now for this meeting. For this meeting, it's just number 1, 2, and 3. Okay. So you need to complete the tutorial to be able to do the assignment. Okay, the group project. Right. So 1, 2, and 3 for this meeting. Number 4 will be the second meeting, and then number 5 will be in the third meeting. Okay. Okay. So again, number You can do if you want. Okay, you can just follow the tutorial step by step. Click here, put your source code in. You can write. No issue, no problem. It's quite short. Okay, the tutorial is not that long. Okay, you can wait, but not required for now. Number 1 and 2 and 3 will be required for you to complete the first project. Okay. So any questions so far? Is that right? Okay. All right. So so if no questions, let me introduce myself. All right. So I've been with UTM. I'm currently leading the research group, VCAT, the VCAT research group, VLSI Embedded Computing Architecture Design at MKE, UTM. And I've been with UTM since completed my PhD around 2014, so now 2024, 10 years. So 10 years, around 10 years. 10 years as a lecturer in UTM. Started this course was started around 2017, around there. I think this course started around 6 or 7 years ago, where we created the curriculum together with Intel actually. Prof. Khalil was there, Prof. Nazir was there, I was there also, with Intel. They wanted a course on software hardware co-design, verification method, and optimization methods. Okay, so we came up with the material, and Prof. Khalil came up with the book around 2017. Okay. So just my background here. Yeah, I actually graduated PhD around end of 2013, okay, around 2014. My undergraduate degree is computer engineering, okay, and then I did my master's in electronics, and then my PhD in microelectronics. Okay, so it's a kind of different area. Computer engineering is more on the, I would say, the top level, right, and then electronics lower level, microelectronics even lower level. Okay, so I basically try to cover the whole range of area. Okay, so which is, if you have to go into academia, is you want to cover a lot of different areas. For example, the master's here, I also take master by course. Okay, master by course in electronics, so we take a lot of different subjects. So from there, the courses that I teach, that the faculty give, also covers basically my background. Okay, undergraduate courses, MKEL, Verilog, VLSI, electronics, digital electronics, postgraduate, VLSI BA, CAT for electronics, VLSI circuits and design, and also this subject, hardware software co-design. So recently, I've not been teaching this subject quite some time. Currently, I'm focusing more on this. Okay, basically, I would say my expertise now. Okay, going into this. Also, my research projects also going more into the implementation. Okay, verification and implementation of hardware software co-design. For the undergraduate, I'm mainly on the DSP architecture 4673 and also year 1 electronics. Yeah, I teach year 1 undergraduate, year 4 undergraduate, and also the final semester postgraduate. So basically, I'm rotating between these 3 courses for now. Okay. Other than that, some of the research that I do. Currently, I'm focusing on the AI machine learning. We're looking at spectral domain. It's a special type of convolution neural network for AI. I also have some projects in high-level synthesis. Okay, and I'm also looking at some of the physical design automation methods and algorithms. So, okay, so this is something interesting here. Some of my students, you can see my previous projects. So I have several PhD students from 2016, master by research. Okay, some of the projects here. I've done some Bluetooth, HEDC video, CNN. So this is a master by course, you guys, in master of engineering here. But I think you guys all have your FYP projects already, right? As a supervisor. Okay, so 19, and then my undergraduate also. Yeah, mainly working on basic FPGA, RISC-V here, physical design, around this area. applications. Okay. Right. Okay. Any questions so far? Okay. All right. So if no questions, let's do the attendance and also. Okay. So when I call your name, okay, if you can just please come to the front. Okay. Come to the front and I'm going to go through the sequence this year. Okay. And just maybe. I need to see some guideline here. Okay, what you want to say? Okay, so just your name, maybe where you're from. Okay, where you're from. And then maybe I want to know where you graduate from. Where you graduate from. Okay. And where working? Where you working? Okay, where's your workplace? And also your what your work department. Okay, maybe you work in automation or verification, or physical design or whatever. Okay, so where you work. Okay, where you work. Okay, your name, where you from, where you graduate from, where you work in Telca, Academica, okay. And also which department. Okay? Boleh? Alright? Okay, so let's call the first one. So Jun Chow. So Jun Chow? Oh, it's not here. Okay. Alright. Number 2. Lim Yong Chua. Yeah. Okay.
Hello, my name is Lim Yong Chuan. I am from Selangor and I graduated from Han University College. And now I'm working in Intel Validation Department.
Intel Validation, yes. All right, good. All right, thank you. Next, Andi Norachikin.
On the way.
On the way. Okay. Later when you come, we will ask you to come to the front there. Okay. Lei Junno.
I'm Lei Junno from Penang. Graduate from Unimed. Currently, I'm working in MKEL technology in Penang as well. A startup company with CMOS image system.
Yeah. Okay. What's the name of the company?
MKEL technology.
Hancock.
Yeah.
Oh, okay. How long have you worked on this company? Is it long already in Malaysia or is it just started? Oh, 3 years. Oh, okay. And the company is doing CMOS
Image sensor.
CMOS imaging.
I'm currently working in the digital design.
Right. Also, startup in the everything, right? Okay. Yeah. All right. Okay. Thank you. Thank you, Long. All right. I did not speak it. So, yeah, boleh. Can you come to the front and just go through here. All right. Name, where you are from, where you graduate from, where you work, and your work department.
Hi everyone, good morning. So my name is Andi Rashid. You can call me Andi. And from
Your hometown.
so I'm from Kota Kinabalu, Sabah. I graduated from Multimedia University. Where you work is in work department validation.
Detail validation. Okay. Detail validation. All right. Okay. All right. Thank you. Okay. Next, Alvin Seth.
Hello, I'm Elvin. I'm from Sarawak. I graduated from Unimas. And I work at Intel as a SC administrator.
It's a civil engineering tech. All right. Next, Ashra.
My name is Ashra. I'm from Selangor. Graduate from NPTI. Working at Now I'm currently at the, I think,
Revision department at least. You have a say at those?
yes.
Okay, what specialization? Continuing learning. Alright, okay. Okay, next, what next?
Hi, I'm Vignesh from Selangor. Graduated from Unitec.
Unitec.
Organization.
Okay.
Working at Twitter. Work department management.
Relation, behavior, alright. Is that?
My name is Idris and I'm from Selangor. I graduated from UTM and I'm working in Altera.
Altera. Okay, yeah, it's,
Altera.
I thought you had seen this before, right? Oh, you are from Sydney? Okay, oh, Altera. Okay. Working in
Physical verification.
physical verification, yeah, Intel Altera. Is it coding or Linux? FPGA, bukan, I thought the FPGA was mainly in kulit, right? Oh no. Kalau tak semestinya. Ini ada juga. Okay, alright, next, Tulasi.
Good morning, everyone. I'm Tulasi. I'm from Selangor and I'm graduated from UTM. I'm working at Altera under verification and validation.
Yeah, we spoke SKL or SKL communication, right? Okay. Alright, Tulasi, thank you. Next, Divya.
Good morning, everyone. My name is Tirsa Dr. Sansaran. I'm from Penang. I'm graduated from ZINET. I'm working in as associate.
SOC. Got it. Okay, good. Okay, thank you. Next, Dr. Dini.
So my name is Nefadini. I'm from Pahang. I graduated from the ITM. I'm working in physical design.
Physical design. Okay. Yang dia macam apa?
The ITM.
Bilang. Chong Sikat.
Hi, I'm Jessica. I'm from Penang. I'm graduate from UTAI and I'm working in Intel Space Design.
Next, Rivenzi.
Yeah, hi everyone, my name is Wendy from Altera. Graduate from USM. Yeah, and so currently work as a product engineer from WD, Western Digital.
Oh, product leader Western Digital. Okay, thank you. Okay, so thank you everyone for the introduction. Okay, we have a quite diverse background and okay, so let's continue with the okay. So the first part of the lecture on the, you can say theoretical part, where you are expected to maybe write a paragraph or give some points, okay, regarding what is SOC. So please take this chapter quite seriously, alright? Later we probably have some activities as well to help you have a better understanding or, to help you later as well with your assessment. Okay, so first of all, what is SOC? It is like a software hardware co-design. So it's basically systems that consist of both a software part and a hardware part. Okay, and when you combine these two together, you call it a system on chip. integrating electronic or computer system onto a piece of silicon, which can include the CPU in there, in the single silicon, the I/O interface, internal memory, and also the other cores. Right? So SoC can include both analog and digital components, and these are normally called the mixed signal system on chip. Right? But in our course, we are not concerned with analog. All right. So we are looking more to what is called the digital SoC. Okay, the digital SoC consists of CPU and the hardware core, controllers, but all in the digital domain. We are not looking at the analog domain. So some of the applications of SoC, you can find SoC in mobile phones. So in mobile phones, for example, the Qualcomm SoC, MediaTek SoC, they call it. So I was at MediaTek for 2 years, MediaTek Singapore, from 2018 to 2020. Okay, so I used to work in the physical design of SoC for 2 years over there. So SoC has a lot of applications nowadays, very relevant. Computers, mobile phones, maybe automotive as well. But the question is, why you want to integrate everything in a single chip and not have a separate chip? Okay, so previously maybe you have a memory, your core, and the CPU on a separate chip, right? Separate chips means separate silicon, but now you want to combine all these components in a single silicon, and the advantage is this one. All right, so lower cost per gate, lower power consumption overall. Okay, if you put everything in single silicon, faster operation, so the communication distance and also the capacitance of the wire also will be less when you have the components all in a single piece of silicon, right? Smaller physical size, obviously, when you combine everything, and also can simplify the board design rather than having multiple chips. Okay, so digital SoCs can be implemented on ASIC, all right, and also FPGA. Okay, so make sure you know what's the difference between these two. Let's go into just a basic flow of the ASIC design. So in ASIC design, we'll start with the design entry on the top. And the design entry is in the RTL language, Verilog, VHDL, system Verilog. You go to logic synthesis, you go to system partitioning, and before that, maybe you need to do a pre-layout simulation as well. And once you have the system partitioning, then you do what is called the physical design, right? The physical design here. And then you have the logical design. So in the industry, normally they call the logical design part is normally called the front-end design, right? The front-end design, the logical design. And then the physical design here is normally called the back-end design, right? Okay. So, and normally in the industry, you will specialize, all right? So for example, I have some experience doing back-end design for SoC, that's done. So working around that area. So just basically, I think you have taken some courses already on design automation, you cover the back-end design flow, and then the advanced digital, you cover the front-end design flow. Okay, so this is ASIC. In the end, your objective of the objective of this ASIC is, in the end, you want to have a design that is ready for fabrication of tape-out, right? That's the last step. So you start with the system spec, Verilog, RTL, system Verilog, all the way up to tape-out of the chip. Okay, so that's ASIC. And then when you talk about FPGA, basically, you can say almost the same flow. It has its own front-end design, back-end design, but now the objective is not for tape-out. So for FPGA design, in the end, you want to program your FPGA, right? You want to generate the bit stream of your design, and then the bit stream will program the FPGA. Okay, so make sure you know the difference between these two. Like for example, okay, so in the front end, it's more or less the same. In the end, in the front end, you want to have your design synthesized to basically gate level memories. But the back end design, the physical design of FPGA basic are a little bit different, right? They're a bit different. Because in one side basic, you want to have a tape-out, you want to go for tape-out, you need to generate what's called the GDS, right? In the end, you have the GDS, and here you have the bit stream. And the way you do the physical design on the FPGA and the custom chip, they are a bit different, right? Or quite different there. Okay, so the flow ASIC FPGA. I'm not going to detail on this one. I believe you all have maybe your working experience and some of your other courses cover ASIC and FPGA design flow. Right, and also here I'm not going to go into detail. Just make sure you know what's the difference. FPGA, for example, the Xilinx FPGA, the Intel Altera. Last time, Lattice came to UTM. They talked to us. Okay, have you heard of Lattice FPGA? Basically, you can say Xilinx is number one. Currently, I think it's a common knowledge that people say Xilinx is the number one in the market share for FPGA. And number two is Intel, right? So are you guys have a plan to take over Xilinx or not? Okay, those are working FPGA. Okay, so Lattice is number three. And Lattice, I think they just started in Malaysia around 2 years ago, 2.5 years ago. And we're currently talking to them about maybe having some of their design kit in UTM. But Lattice has been around for quite some time. They just started in Malaysia around 2-3 years ago. Okay, so FPGA that. Advantage mainly is fast implementation design, right? Fast time to market. Or you can do prototyping before you go ASIC. Okay, that's the purpose of learning why we use FPGA. ASIC, best in terms of power performance area, cost per chip, in terms of power consumption, performance is the best. Okay, I think cannot beat any other platform. You cannot beat ASIC. Okay, that's why, for example, your MediaTek SoC, Qualcomm SoC is in the ASIC technology, right? It gives you the best in terms of PPA. Okay, so this is the advantage, disadvantage. This is something interesting that I took from the IRBS 2023 about the flexibility versus efficiency of the implementation platforms. So what does it mean by flexibility? What does it mean by efficiency? Okay, so flexibility, you talk about maybe the programming language, for example, C++, if you code in Python or C, immediately you can run. Immediately you can run on a laptop, or maybe you run on a embedded device, very fast and very easy to run. However, for ASIC, okay, the least flexible, right? The least flexible. If you start from RTL, how long does it take until you get your chip? From RTL, how long does it take until you get your physical chip with the packaging all tested? Okay, maybe half a year, right? 6 months to 1 year, or maybe more, right? Just to get it tested. Okay, as compared to here, immediately you have your C program, immediately you can run. Okay, so that's what you mean by flexibility. And then efficiency in terms of PPA. Okay, power performance area. ASIC will give you the best in terms of performance, power area, and CPU relatively will be less. Okay, in terms of performance area. Okay, so make sure you can, if I give you this figure, you can explain a little bit in one paragraph. Okay. Alright. So SoC. Okay, so going back to SoC, so what is SoC? Is a single silicon, a single chip that combines the CPU and also the other peripherals, controllers and hardware core. And we can implement SoC inside the ASIC or FPGA. Okay, so in this class, we are not doing ASIC. Okay, so in this class, we may be going to use Xilinx two chain. So we will not talk more about the FPGA-based system on chip. Okay, so these are the advantages. It's already covered in the previous slide. So for example, here if you have a FPGA system on chip, okay, you have a CPU core there. You can see the CPU core is connected to a system bus, and the system bus is connected to some other peripherals, such as the hardware accelerators, some IPs, communication protocol, I/O systems, okay, all in a single chip. Traditionally, maybe you have your hardware accelerator as a separate chip, okay, not in the single silicon. Maybe your memory system is also a separate chip, right? So here we talk about software hardware co-design, whereby you have your CPU, memory, core, I/O systems all in a single chip or single silicon connected by a system bus or peripheral bus. Okay. So one thing to note here, in our class we are not going to design this. Okay, we are not going to design this. It looks interesting. Okay, but this is later we see this is called a platform-based design. Okay, we're only going to look at the theory of how to implement this. Okay, but our class is more focused on verification of the hardware accelerator, okay, using the CPU. That's one. Optimizing the hardware accelerator in RTL, okay, and also implementing hardware accelerator from a high-level language. Okay, so we are not really looking at the system bus. For example, what's the example of system bus? You have the IPB, right? The IPB bus, political bus. So you have a several system bus, specific platform-based bus that you can use. But we're not going to go into detail on the bus standards, interconnections, or communication between the cores. Okay. Okay, let's look at the SoC design approaches on the theoretical side. So we start with the RTL design and synthesis. That's number one, the front end design. Designing the hardware core and the accelerator. And then we have the high level programming models to program the CPU and GPU. We also can use the C program to perform high level synthesis and implement our hardware core. Right? And then when we talk about designs, there are core based and platform based design. So you can have a core based design where your SoC consists of IP core that you can design yourself or you can buy from outside. Right? So that is a core-based design using IP cores. And then there's something called the platform-based design, which is vendor-specific SoC design. So you have, for example, if you want to design for Intel FPGA SoC versus Xilinx versus Lattice, they all have a slightly different approach, right? Maybe the bus protocol might be a little bit different. Sorry, the APB bus, not IPB, APB. APB bus. Okay, APB bus is a standard bus protocol, but it might be a little bit different depending on the vendor. Okay, and also the CPU that's being used by the vendors are also different. Okay, maybe some vendors they use ARM, some vendors go into RISC-V. Okay, so different CPUs, different platforms. So the way you design is maybe also a little bit different as well. Okay, so platform-based design. Okay, so what is hardware software co-design? It's a design where we incorporate the hardware and software components in a single design flow. Because software is easy and flexible, hardware is not as easy to design. Okay, writing RTL code is generally, you can say, is more difficult, right? You have the CU, DU. Take the example of the sorting algorithm, right? If you have done sorting algorithm in C, C++, very short, you can do it very easy. Okay, maybe you can do it 20 lines, 30 lines. But how many lines in the same algorithm in C? Let's say bubble sort in RTL. How many lines you have in RTL for bubble sort? Okay, you have the CU, you have the DU, right? You have the top, you have to combine together, you have all the interconnections, you have the clock, you have the reset. Okay, so generally you can say RTL hardware is more difficult to design, it takes a longer time. But is it worth it? But you can see that hardware, ASIC, FPGA will give you a better PPA, right? Better performance, power, energy, as compared to a quick design in software. Okay? So how to get both sides? I mean, you want to have a quick design. You want to have a quick design with also good PPA. So what is the solution? So the solution is, they say you use the high-level synthesis methodology. Okay, that's one solution. So you can design your sorting algorithm in C, okay, and then you use the tool to automatically get your RTL. So no need to write manual RTL. Okay, you use the tool, you get it, you get RTL, sorting algorithm, I think like 10 seconds, okay, you get your RTL, all right? But is it efficient or not? That's another question, right? Is it more efficient to write your RTL manually? Okay, or you generate your RTL from C using these tools. Which one is more efficient? So also to find the balance there, right? You want to write everything in RTL from scratch, it will take a long time. Okay, or you want to use you want to just write in C and then use the tool to generate RTL. Okay, and then see if you if you get your if you achieve your objective in terms of your performance, power and area. Okay, if you achieve it, no issue. Okay, just write in C, you achieve your PPA requirement, then you can forget about RTL, right? But if it's not achieved, okay, if it's not achieved, then you have to write your RTL manually, right? Okay, so SOC co-design flow. Specification and modeling, we start with the spec of our system design. Let's say you develop some AI, maybe some AI model to classify something, to recognize, let's say facial recognition, or handwritten recognition. Okay, so you have some specifications, some design that you want to implement, you want to run. So first you need to select your platform first, right? You want to implement this AI on the Raspberry Pi, okay, on the CPU, on your laptop, or you want to run it on the FPGA, you want to create a custom chip. Okay, so select the platform. But first, normally you start with the pure software implementation to verify the algorithm. Okay, you don't write the RTL straight away, right? Because it's very long, you need to understand how the algorithm works. So maybe you write in Python first. So Python will probably give you not so good performance, so maybe you go to C. Alright, Python to C. There are some tools, I believe there are some tools to convert Python to C. Even Python to Verilog also, I see some tools. Okay, converting Python to Verilog, so you don't really have to write manually. But in any case, you will start with software. Okay, something complex. If it's something easy, you can straight away write the RTL. But even sorting algorithm, you start with software first. Then you will profile, the number 3 there, you profile your software performance. Which part of the software is slow? That is a bottleneck, right? Or something that you can see you can make parallel. Okay, that part is the part where you take and try to implement on the hardware side. Okay, on the FPGA or create a custom chip for it. And the rest can be can go on software. Right? So we break up the design. Okay, maybe if you have a camera interface, the camera controller might be suitable on the software. Okay, the memory controller, which is sequential, the camera controller sequential, those can go into software. But the actual AI operation like convolution, repeated arithmetic normally can go into hardware because you can do parallel. Okay, so you divide which one should go software, which one should go hardware. Okay, so once you have your hardware design, you have your software design, then you need to make the interface. Okay, the interconnection using the bus, the APV bus and so on. Make the interconnection between the design. This is the I would say challenging. It's based on the platform, but it's a challenge to make the synchronization between software and hardware. That part is not that easy. It's a lot of engineering work, okay, that needs to be done. Not really research based. Okay, it's more like this area interface design. How many pages is the memory controller? For example, on the APB controller, it's quite thick. There's a lot of anybody have experience designing bus? Yeah, anybody pernah buat bus design tak? I think like 200, okay, 100 plus 200 pages on the bus protocol saja. Okay, the bus protocol. How do you send your data to the bus? Okay, all the signals, the synchronization signals. So a lot of things that you have to read through. Okay, if you want to make the interface. So that's why we don't really cover in this class. It's more technical. You just need to read the manual. 200 pages with waveform on how to interface your module with the CPU using the APP, for example. Okay, so once you have verified this, okay, then it's time for integration and prototyping. Okay, integrate everything, prototype, implementation testing, and then you can install your product. Okay, so this is the code design flow. Okay, so now the question is, what should we design in hardware and what should we design in software? So imagine you have a CPU and a hardware simulator in single SIM card. Okay, so So which part should go in the accelerator, which part should go in software, and the rule is, or you say the optimal way to do it is anything that is software, software. So anything that is complex, very complex, is low throughput, sequential, and generally as much as possible, okay, should maintain in software. Okay, that's the rule that they say. And what should be the hardware is the algorithm kernel, so like a convolution operation, you have a lot of multiply add. Okay, multiply add. If you have a lot of kernels, you can make the kernels in parallel. Any compute intensive functions, computation centric, bit oriented. Okay, like the floating point is bit oriented. You cannot really do floating point software. Okay, that's why you have a special floating point unit. So anything that is a lot of computations that you think you can do parallel, you should go to the hardware side. Okay, so our course actually focus more on the hardware side. Okay, it's a hardware software co-design course, but we are focusing on the top part there. Alright, so first we look at the verification of hardware systems, using C. Looking at how we can optimize our hardware design, okay, and looking at how we can implement our hardware design using software. Okay, so that's the scope of our course. Okay, so this is a very interesting figure, not very clear here, but it's a figure that I've taken from the IPDS just now. Okay, the roadmap for device and system, where they say that it is expected that we are going into implementation whereby we are going to offload some parts of the processing in the CPU GPU to a custom silicon. Okay, so I think this is what's happening in the industry as well. But I would say mostly still running here. Okay, most of the systems, AI systems and so on, from what I observed, in my opinion, still running here. Okay, not many are going into here yet, not yet. Okay, but the roadmap, which is set by some experts, mainly from the US and Japan, mainly from US and Japan, they envision that in the future we'll have more applications or more of the computations or operations will be offloaded to the custom silicon. Okay, as a hardware accelerator. But currently I think most of it are processed here. Okay, because the CPUs and GPUs currently they're not too slow, right? I mean, if you talk about your phone is very fast. Okay, but the phone is a SSD. Yeah, I mean your Intel CPU is not slow. Okay, Raspberry Pi ARM-based CPU also not that slow. But in terms of PPA, okay, in terms of performance, power area, especially power, if you talk about power, for battery power device, we want to move to the custom silicon. Okay, on FPGA or ASIC. Okay. Okay, this is an interesting figure of the system design R&D flow. Okay, I believe if you work in the R&D side, the industry, or even if you're as a postgraduate student in our lab, okay, basically what we do is this, right? We have a system spec, okay, let's say some AI algorithm. Make sure it functions well first. Functionality is number one. Okay, does it work or not? So once it's working, you have the baseline implementation, then you think about the optimization, either on the algorithm side or on the architecture side. Okay, so this is what we look at. Maybe in the second part of the meeting. Okay, second part of the meeting, we look at the and mainly we are going to look at the architecture. Okay, architecture optimization for PPA for our second meeting. Okay, for the first meeting, we are looking at functionality. Okay, how to verify your RTL. Okay, verify your RTL using C program and also System-Verilog. Okay, optimization, and also the third one is looking at the design. So the last meeting looking at the blue color. So you can say the first meeting is the green color. Okay, second meeting the orange color, and then the last meeting we look at the system type and design. Okay, but with some optimization as well. With some optimization as well in the third meeting. Okay. Okay, so the last part on the platform-based design. Last part on platform-based design. So we have the Intel SoC FPGA platform, and we have the Xilinx SoC FPGA platform. So I'm not going to go into detail on this one. There's an example here. This one is taken from the from the Intel side, okay, Intel FPGA side, where you have in a single silicon, they have the FPGA. Okay, in a single FPGA chip, they have the configurable blocks, the configurable logic blocks, the FPGA, and then you have the hard processor system. You see the CPU side. Okay, so there's the CPU, the FPGA, maybe your algorithm kernel and all can go here. Interface with the hard IP, PCI Express, transceiver, memory controller. Okay, so they have the IP here, they have the CPU, they have the configurable logic blocks. Okay, all in a single FPGA. Okay, so how to design this is very technical. So we are not going to go into detail in this class. Okay, but I think if you work as an engineer, you know, application engineer, that you need to develop some SoC applications, you know, the memory controller, you know, you have the manual, you have the standard. Okay, PCI Express, you have the standard 200-300 pages, right, that you have to read through. Okay, how to send the data, so you compute some data here, how to send to the PCI Express bus. Okay, this one will go to PCI Express, alright? So there is a protocol, you cannot just simply send data, right? You have some control signals here that you need to follow. The timing you need to follow, you cannot just simply send however timing you want. Okay, it must be some protocol, okay, how we bit and so on. Okay, so it's very, very complex, PCIe punya bus. And also memory controller, also very complex bus. Okay, interfacing between FPGA and the hard processor, you know, example using ATP bus. Okay, also quite complex as well. Okay, but for us, we just need to know. I mean, you know, just know the theory of SoC design. Okay, we're not going to details. We are not going to details on the specific bus implementation, but just know the theory that, you know, FPGA SoC inside there you have the configurable blocks, CPU, and also all the other IPs for controllers. Okay. So this is the Intel, and similarly you have the Xilinx, the same. Okay, more or less the same. Okay, not exactly the same, but more or less the same. You have the FPGA side, or they call it PL. Okay, in Xilinx they call the programmable logic, the PL side, and up here they call it PS. Okay, so the concept similar, but of course a different terminology. So here they call PL, PS. So in the PL you have this you have the DSP, high speed multiplier. You have maybe the block RAM inside there, configurable blocks inside here. Okay, some sensors, PCIe, IPs inside there. Okay, interface with the PS. So PS is your CPU. Okay, your CPU. Second, Xilinx using ARM. It's an ARM-based. So this CPU is actually hardcore. It's a hardcore CPU inside the FPGA. Alright. You can also create a softcore CPU, right? Softcore CPU. So you have the RTL of the ARM. You can program your CPU inside here. That was previously they used to do this several years ago. Where you don't have a hardcore PS, you have if you want to implement a CPU, you have a softcore CPU inside the PL. Okay. But nowadays, you know, CPU is used quite frequently in the SoC, so they put a hardcore processor. The same way they put hardcore CPU inside the FPGA to interface with PL. Okay. It's an ARM Cortex A9, for example. It's an ARM Cortex A9. It's a hardcore ARM CPU. Okay, so just one side note, the ARM here is not free. That's the issue, and then from there, you know, the RISC-V, you heard of the RISC-V CPU. So the current trend is going into the RISC-V. Pernah dengar RISC-V? Pernah. So the current trend is going into the RISC-V CPU. because the RISC-V CPU is open source, right? We call it open source. Betul? I think so, right? So you can get all the libraries, you can customize your CPU as compared to ARM there, it's a little bit not flexible. Okay, so there seems to be the industry trend is going into the RISC-V CPU core. Okay. Okay, so any questions? Any questions on the SoC concept, implementation platforms? Okay, if no questions, then we have activity. Okay, so in groups, okay, in your group, I'll give you 10 minutes. Yeah, give you 10 minutes to discuss with your partner or groups. Okay, maybe 3 or 4, right? 3 or 4 students per group. Okay, so let's see what you have to do. Alright, so when you talk about electronic systems, you can implement, okay, so let's say AI, let's say AI or sorting algorithm or whatever system you want to implement, you can implement on CPU, okay, on your computer, your laptop, you can implement on embedded systems like the Raspberry Pi, Arduino and so on. You can implement as a ASIC chip, you can implement on FPGA, you can also implement as a combination of hardware and software. Okay, in groups of 3 or 4 or 2, doesn't matter. Okay, so just briefly explain the design flow. Okay, if you turn FPGA, what is the design flow of FPGA? Okay, if you try to design using the embedded processor, embedded system like the Raspberry Pi, what is your design flow? Okay, and then describe the advantage of your chosen platform. If you choose FPGA, what is the advantage of FPGA implementation as compared to ASIC? Compared to, just compared to what other is enough, compared to CPU, compared to your laptop, and so on. Alright? Boleh? Okay, 10 minutes. You can use ChatGPT, you can use Google, okay, e-miners also. Okay, this will help you later. Later tomorrow, we discuss some test questions. Okay, this is the type of test question that we make. Okay, that you have to just explain in one paragraph regarding the SoC concept. Okay, so the design flow you can find up here. Okay, I have my design flow here. So this is SoC design flow, the FPGA design flow, okay, and the ASIC design flow. Okay. Okay, so 10 minutes, 10:30. All right, so let one speaker, one volunteer to speak. Siapa nak speak? Alright. So one speaker, you just 2-3 minutes is enough. Okay, 2-3 minutes. Just talk about your platform, how you implement it. Okay, and the advantage of your chosen platform. Okay. Siapa aku kena buat? Okay, yang saya okay, you implement dekat FPGA dengan Raspberry Pi sama tak? Tak sama. Apa yang berbeza dia? That's why example. Compare dengan apa-apa. You pilih satu, and then you compare dengan apa-apa satu lagi. Okay. Okay, so one group, satu group mungkin 4 orang pun boleh. Okay, 1, 2, 3, 4. Alright, boleh. Okay, select one speaker. Okay, nak buat asing ke tak sekali? Ataupun nak 3 orang pun boleh. Dua. Nampak 2 boleh. You nampak 2 orang? Nampak orang pun boleh. Nampak orang, 2 orang boleh. Nampak orang nampak orang yang sangat pun boleh. Okay, boleh. So, kita ada 3 group. Boleh discuss. And then select one speaker who is going to speak. Okay, and just 3 minutes. Okay, 3 minutes. Just talk a little bit about your. Okay, faham kena buat apa? Faham It's subjective. This thing is subjective. I mean, just can talk about anything. It's a big area. You know, you can talk about specific platform. You want to talk about specific applications, your experience. So it's subjective. Anything you want to say about, implementation platforms, advantages, disadvantages. Okay. We have a volunteer from the three groups. Want to start first? so ni group 1 group 1, group 2, group 3. Alright. I will choose randomly. Okay, we use a random number generator. Normally you don't know what to start. Okay. 1, 2 or 3 Okay. Atau ada volunteer? Tak ada. Kalau tak ada volunteer, normally I like to use the random number generator. Let me use a random number. So 1, 2 and 3. Random. Okay, ready? Okay, group 3. Group 3 first. Okay. Okay, can you come to the front?
So we are just search on the image processing. Okay. So basically we are focused on the image processing on FPGA and also the CPU. Okay. So from what we can search, the pros of the processing on the FPGA is the parallel process. Because some of the algorithm will be more complex if we can add or multiply at the same time parallel. So it will make the total processing time faster in the FPGA. Yeah, it depends on the FPGA technology. It's more towards the parallelism compared to the CPU. Again, is the pros of the FPGA is the power consumption. Normally FPGA is designed for low power compared to the CPU. It's multiple function peripheral connected to the CPU, so it will consume more power. Even we don't use it, it will like normally will activate it, but yeah. So, but for the cons of the FPGA is more complex in the program because we need to write in RTL, not the CPU. Normally we can use multiple language, maybe C, Python or something. We can directly access with even our laptop. We don't need extra tools or something for it. For FPGA, like we need to download the tools for certain FPGA. So even for the CPU part, we can directly online get the programming parts to do all the things. Okay. Any other things? Then the FPGA cost of FPGA is the cost. Yeah, the cost is more expensive compared to CPU because it's designed for certain purpose for like there's only for all the parallel processing and also for industrial. Normally we don't use FPGA in our life. Yeah, so but the CPU, everyone has the laptop. You can just bring your laptop. You do the programming on the whatever you want. You do the processing on the online or software. You can directly get it. So for FPGA, it will cost more.
Okay, good. So it seems you guys understand what FPGA is all about, and image processing algorithm. The power is interesting. Why the CPU has consumes more power than FPGA? So you mentioned regarding
all the IOs, all the connection. Even we don't use it, will activate all the like.
It activates all the time.
Okay. Memories.
Okay. So yeah, one thing is CPU, the frequency is higher, right? The clock frequency is higher, and then also because the CPU is bigger, right? There's more logic compared to FPGA. So we talk about power, you need to see why the FPGA consumes less power as compared to the CPU. Okay, there are several factors there, right? So very good. I think very good for group 3. All right. So next, anyone here for group 1 or 2? Okay, example random. Random, okay. So, okay, group 1.
Okay, so for our team, we chose ASIC to elaborate. Okay. So for ASIC, in contrary to FPGA, the ASIC requires to for the entire design flow of the SoC. First, we start with front-end design, which is the hard IP or soft IP, which is the RTL. Then we will proceed to, after for soft IP, we will need to go through the verification and synthesis process. Then we will pass the front end designs like the hard IP and soft IP to the back end, which is the physical design. Then they will do the floor planning, they will do the placement and do the routing. And they will they run through a closed layout simulation and compare with the pre-layout simulation. If the specs still fit, then we can proceed to the fabrication. So this is actually the closed layout and pre-layout actually comes back and forth, so it requires a lot of slack time in the design. And for the FPGA, it's just from what I heard from the experts, because I'm not an FPGA expert, I'm not an expert. It's like more flexible. So what I heard is that if one FPGA, the I/O is not enough, we can cascade the multiple FPGAs, so it's more suitable for. Yeah, I just learned that. It's very interesting. And for ASIC, it performs a specific task scatter. Like for instance, in the TPU, tensor processing unit, we got an ASIC. I think it's considered ASIC, which is a matrix multiplication unit. It just do a specific task as in the matrix multiplication unit. So it's more specialized in terms of power, performance, and area optimization. And the advantages of ASIC is like its flexibility in physical design. You can customize how much I/O, how much GPIO, how much power and area, like always more customizable in terms of, as long as you hit the specs.
Compared to FPGA.
Yeah, compared to FPGA. Because FPGA you might have when you cascade FPGA you might have some redundant RAM or redundant I/O speed.
Yeah, that's a good point.
And FPGA, you do not need a huge manpower in terms of like this my personal opinion might be wrong, because for the entire ASIC you need a vast amount of verification for RTLs and a huge amount of manpower for the layout and
I think it's right. Yeah.
But for FPGA, there's no post layout or something or the methodology. So FPGA verification or implementation FPGA is more faster and more requires less manpower and cheaper in terms of corporate execution and others.
Yes. Good point. Interesting point. Okay, very good. In terms of manpower, it's correct actually, right? I mean, because to do the whole ASIC flow, you need a lot of engineers at all stages. Okay, including the fabrication one, the tape out one also need people there. So that's a good point. And also a good point about the cascading the FPGA. Because normally you can say that FPGA you have limited I/O, right? In ASIC you have unlimited I/O. Theoretically unlimited. But actually you can cascade the FPGA to make it unlimited as well, right? It's an interesting point. Okay, very good. So let's go.
Hi everyone. So I'm from group 2. So we are our comparison is FPGA vs ASIC. So the design flow implementation. So it starts with the specifications. Means that we need to define the functionality and the requirement of our system. Next is the high-level design, in which this is involved the HDL, like variable VHDL. Then the second stage is the synthesis. So from the high-level design, we need to convert into the net list of logical elements and interconnections. The next one is the implementations, in which it placed and wrote the logical element into the physical FPGA device. And the next one is the configuration. Configuration is where the stage of we load the design into the FPGA device itself. And the last one in testing and debugging. So testing and debugging, we need to verify the functionality and the implementation system, and if there is any issue in the FPGA, we need to debug. Okay.
Okay, alright. And advantage?
So the next one is the advantage and disadvantage. So this is we compare the advantage of the FPGA with the ASIC. So the first one, the advantage of the FPGA itself, it has a flexibility. It means that FPGA can be reprogrammed multiple times. The ASIC cannot.
Good point, good point. I think you guys missed that point, right? Yeah, because there's a lot of points. So I think good, it's separate points. You can program a lot of time. Okay.
Okay, so the second one is the time to market. As we see, FPGA is a shorter development cycle compared to ASIC. The next one is it has a lower and NRE cost. And the last one is NRE cost.
So you say what's NRE? What is NRE? Maybe explain to everybody. Non-recurring engineering, so what it means? One-time cost. Basically, correct?
Yeah. And the last one is on the prototyping. So actually, FPGA are ideal for prototyping and proof of concept development, enabling the designers to quickly validate their ideas before committing to ASIC fabrication. Okay. So next is the advantage of the FPGA compared to ASIC. So the first one is it has a higher unit cost, as we know, and next one is it has a limited performance, right? FPGA generally have a lower performance and power efficiency compared to ASIC tailored for specific applications. The next one is the resource utilization. FPGA design may be required more design, logic cells, memory blocks compared to ASIC. And the last one is has limited stability.
Limited stability.
Yeah.
For FPGA.
Yeah.
Okay. What do you mean by limited stability? I just got it from ChatGPT. I would say limited stability. So I mean the design can be stable for both. What do you mean by stability? Scalability, yeah, okay, scalability, correct. But stability, I think both should be stable.
Yeah.
Right. Okay. So, okay, what it means by scalability?
Limited performance and power.
Okay, correct. So yeah, I mean, yeah, in terms of scale, because you have all the other components as well inside the FPGA, right? ASIC, they're custom, right? You just fully custom. So, other interesting points from your side. Regarding the yeah, you talk about time to market. What is the other advantage of FPGA? Prototyping, right? So FPGA normally normally people use for product boleh juga directly the product or prototyping. We talk about prototyping before going to ASIC, but you can also use FPGA as a real product, your own product as well. But the PPA will be less compared to the ASIC. So, okay, very good. Thank you everybody for your good contributions to our first class FPGA. Okay, so let's pause the video. You can see. Right, 1 hour and a half.